on the Lunar Gateway program. And I want to talk this morning about assumed guarantee contracts and their use for operational verification of autonomous spacecraft. Before we get into that, I really do need to acknowledge and express appreciation for three groups of folks who were really contributed significantly. I get to present, but they did a lot of the hard work. And that includes my colleagues, Dr. Jim Dabney and Dr. Julia Badger, who were really instrumental on having the vision for the maturation and implementation of runtime verification on Lunar Gateway, specifically on VSM. Also, Dr. Kristen Rosier and the team at Iowa State University, who developed and maintain RTU2. And then also the VSM flight software team that's really worked very hard to understand RTU2 and then implement it, actually get it working on target software, target hardware, and target software. So just appreciation for those. So an overview, I want to give you a little bit of the background and motivation for assumed guarantee contracts and operational verification. Give you a little bit of definition for what assumed guarantee contracts are and the format for them. How do we define them? How do we select what is appropriate for assumed guarantee contracts and for runtime verification? And then how do we actually implement them, the architecture that we're using to implement operational contracts? And then the workflow that we are using for developing, testing, implementing, and actually exercising assumed guarantee contracts in operation. And then wrap up with some just results, what we've been able to accomplish to date and what we are hoping to accomplish in the near term in the future. So the Lunar Gateway is essentially, you could think of it as a space station that orbits in cislunar orbit around the moon. NRHO means near rectilinear halo orbit. It's sort of an out of the plane orbit, which enhances or limits the amount of eclipse time and enhances the amount of time that we can actually communicate with the gateway. The approach that we're using is to gradually build up the gateway, kind of a similar approach to what was used on ISS. The initial phase is the co-manifested vehicle, and that is two modules that are attached together. One is the habitation logistics outpost. The other is the power and propulsion element. And that is scheduled to go in sort of the 2025, 2026 timeframe. But after that, there is a sustaining phase, which extends for an extended period of time. And other modules will come up, International Habitation Module being developed by ESA, the airlock module, the robotics, the refueling module. There's several other modules that will come up. And then also there will be visiting vehicles that come and dock with Gateway, Human Lander System, the Orion, the logistics module, and so on. So as most of us are aware, exploration spacecraft are becoming increasingly more complex and also having a greater need for autonomy, because certainly there'll be a greater need for autonomy with Gateway than there was with the International Space Station. There are a number of reasons for that. It's expensive to monitor a space station 24/7, and that's not the paradigm that NASA envisions for Gateway. So the Vehicle Systems Manager is an overarching command and control system, you can think of it, that coordinates the activity of the command and control systems on the individual modules. Each of those modules are, they're not being developed from scratch, they're being repurposed, existing modules. They all have their own command and control system, but there is a need for an overarching Vehicle Systems Manager that controls and coordinates the activity of those individual modules. One of the things that it needs to be able to do is to manage an unattended spacecraft. Unlike ISS, Gateway is going to be unmanned for the majority of its life. We are envisioning, perhaps crews visiting there once a year, or perhaps even less often. So you're talking about periods of longer than a year during which there is no human presence on the Gateway. It needs to be able to monitor and coordinate multiple subsystems It doesn't do that directly, but it does that through the module system managers. Module system managers are essentially subsystems that are the brains of the individual modules. And it needs to be able to vary the level of autonomy, everything from direct human commanding, where there is very little to no autonomy, all the way up to essentially where the vehicle systems manager takes care of things and just provides reports, once in a while, once a week, about things that are going on. So that autonomy needs to be able to be varied. So just to kind of an overview of vehicle systems manager, there's 4 management functions: mission and timeline management, resource management, vehicle control and operation, and fault management. VSM also is the interface essentially for humans, both ground operators and onboard crew. As I mentioned, it can go from fully autonomous when uncrewed to and with no active ground control, but also it needs to be able to work in a collaborative sense with either onboard crew or ground. And we need to be able to verify that level of autonomy to support, however, ultimately humans are in charge. And they need to be able to accomplish what they need to be able to accomplish, but at the same time, when they need assistance, we need to be able to provide that to them. So that's part of the challenge, is being able to sort of adjust the level of autonomy on the fly. So for all these reasons that I've mentioned before, there is a really a need for enhanced insurance. VSM is going to, because it's operating in an environment that we have not, humans don't have experience operating in, that there is a good likelihood for unexpected situations. We're not going to be able to plan for every contingency. There's going to be environmental anomalies. There's going to be system anomalies. There's going to be system failures. VSM has to be able to stay within certain boundaries. We can't predict a priori or dictate exactly how it behaves in every situation, but we want to know that it's going to be safe, and that if something goes wrong, that we can recover it, get it back into a relatively safe state, and then continue on. So that's where assumed guarantee contracts come in. Assumed guarantee contracts define the expected behavior of systems, subsystems, and components. One of the things that we are doing is the architecture of VSM is intended to be modular or component-based. VSM itself is software, is component-based. It's developed on CFS with individual applications. And then in addition, VSM has defined interfaces with module system managers. There's a defined level of authority and roles and responsibilities for module system managers and what VSM needs to do. And they interact with each other using across commands and data. So there's a good sort of division of responsibility. So getting back to assumed guarantee contracts, the assumptions or preconditions on the subsystem's inputs bound the conditions in which the contract applies. So the contract does not apply all the time. If the assumption is met, then the contract should be met. And the guarantee is, or the postconditions, is the condition that must be satisfied, the output must be satisfied in when the assumption holds. And they can be, you can think of those as verification goals. Contracts can be used to define safety or safety properties or hazard controls. So just as an example, a terrestrial example would be a car should not start unless the transmission is in park. So the assumption there is that that if a car is starting, right, the guarantee is that it has to be in park mode. The nice thing about assumed guarantee contracts is that they can be converted into a mathematical specification, and that mathematical specification can be exhaustively model checked to make sure that the system has the desired behavior and safety properties. So on VSM, we have internal contracts that define the interactions between the applications or components that make up VSM. We also have contracts between VSM and other external entities, primarily MSMs. The sources for those contracts vary. In the case of internal contracts, they are derived from requirement specifications and different scenarios and use cases. You can essentially think of those as watchdog type functionality for the VSM software. The MSM contracts are defined in interface control documents, and primarily it's the responsibility of the module provider, the folks who deliver the modules and the module software, to ensure that their system and subsystems comply with those assumed guarantee contracts. However, it's also incumbent, there's an onus on VSM to also monitor those contracts and detect if there are violations and take actions. One of the things that we wanted to come up with was a succinct way of defining and capturing assumed guarantee contracts. And so this is the template that we are using for essential components. You know, what are the variables that go into these assumed guarantee contracts? Those include the input and output variables and the data types associated with those. And then the assumption, which is the condition or constraints under which the contract is valid. And then the guarantees, the conditions or outputs that must be satisfied when the contract is valid. So this is the template that we're using. For an autonomous system like VSM, the set of possible assumed guarantee contracts that you can define could be unbounded. It could be very large, but eventually, at least a good subset of these assumed guarantee contracts we want to implement operationally, and even the ones that we want to check in development time are expensive. It's expensive, time-consuming to define the contracts. It's very time-consuming to verify those contracts, and so we need to have some criteria to decide, you know, when is it worth defining something as an assumed guarantee contract, because there is cost associated with defining and verifying those. So we define 3 selection factors for when we're actually going to define something as an assumed guarantee contract that we're going to expect to be verified, because the idea is that everything that we define as an assumed guarantee contract is either going to be verified at design time or it's going to be verified operationally. So the 3 factors that we're using, we want to sort of limit or bound assumed guarantee contracts to mission or safety critical behavior. We also want to look at behaviors that are not covered by our fault management engine. So VSM, as I mentioned, there's 4 areas or applications, fault management being one of them. We do have a very robust and capable fault management engine that is capable of discovering or detecting things. But if there's something that is not covered by that fault management engine, then we want to include it in an assumed guarantee contract. And another selection factor, and sort of you'll see this as we go into the rest of the slides, is that contracts that involve temporal behavior, so there's a time element to it, those are good candidates for assumed guarantee contracts. So this presentation really primarily focuses on the operational verification, but there is the potential for developmental verification of assumed guarantee contracts as well. And the way to do that, again, I won't get too much into it, but the way to do that is you can create abstractions of your system or software. And the approach that we used is to depict them as, describe them as state machines. And you can use modeling languages such as Promella, or the one that we used is TLA+. And so you describe the system as an abstraction using a state machine. And then the contracts themselves, you can describe using temporal formulas and model check them using a model checker such as SPIN or TLC. And that's developmental verification. Now the operational verification, which is sort of more the focus here, that's actually performed at runtime. So when the system is actually operating. The difference there is we're not talking about an abstraction or a state machine representation. We're talking about the actual system. That's the system that we are verifying in real time. And it's feasible to implement contracts, and people have implemented contracts using inline code, or the approach that we used is to have a separate runtime verification engine such as R2U2 that is able to independently monitor your system and check for violations of contracts. So there's two types of logic that assumed guarantee contracts can use. It's propositional logic. Propositional logic uses the current state of the system. So a propositional expression would be A and B. That is true if A is true and B is true right now. There's also temporal logic, which has a time element. So if you see that diamond, what that means is that it's an eventual operator, right? It may not be true right now, but at some point in the future, A and B are going to be true, and that's going to be true. So that temporal formula is true if at some point in the future, A and B are true. And you can also have temporal operators that work in historical time as well. Now, both types of logic can be coded in C, but some of the challenges there, temporal formulas are difficult to code. They are error prone. Historically, we've seen that. They are very difficult to test. In order to test it and be really assured that you've implemented it correctly, you need to run a lot of test cases. And so we found that a separate engine, R2U2, which I'll get into a little bit more in the next couple of slides, provides a much more reliable approach to implementing these assumed guarantee contracts, particularly the ones that have temporal logic. So some of the advantages, we actually did a trade study. We compared different types of runtime environments, runtime verification environments. And some of the advantages that we found for R2U2, the temporal formulas can be expressed using precise, unambiguous mathematical notation. So we're not talking about natural language, which has its limitations, but we're talking about precise mathematical expressions. R2U2 itself has been optimized. It's very compact. Doesn't take up a lot of memory space or a CPU. It's been used on remote operated aerial vehicles and other types of robotic applications. It's been used on some of the robots at JSC as well. R2U2 has a core inferencing engine, which is the engine that evaluates the temporal formulas based on externally supplied signals, and that engine has been mathematically proven correct. And that is really the most complete form of verification. It's a higher form of verification than what we can achieve via traditional testing techniques. And that was one of the main drivers for us selecting R2U2 as our engine for evaluating temporal formulas. So here, this slide depicts sort of, in an abstract sense, the implementation architecture. So you'll see on the left side, there is software that the VSM team has developed and implemented. In the middle is what's supplied by Iowa State, the R2U2 environment, and then the output is being verdicts. So to kind of go through this slowly, the way that this works is VSM flight software and the module system managers generate telemetry. The VSM team developed an application called the Runtime Monitor, which essentially acts as the interface between VSM, which is running in real time, controlling the gateway, and the R2U2 environment or the engine. What the Runtime Monitor does is it captures the relevant signals, the signals that are needed inputs to the temporal logic formulas, and it passes them to an atomic checker. R2U2 does not process the signals in its raw form. It converts them into Booleans, and that's what the atomic checker does. It is guided by a set of filter commands that tell it how to process those signals to yield a set of Booleans, which is then an input into the R2U2 engine, inference engine. The inference engine is driven by a set of mission time linear temporal logic formulas. Difference between linear temporal logic and mission time linear temporal logic is mission time linear temporal logic is time bounded. So, for example, I showed you that formula, eventually A and B are true. Well, that's unbounded. That can't be evaluated in real time. So the sort of an equivalent formula would be eventually between now and the next 10 time steps, A becomes true. So there is a time, there's a bound that MLTL does that that allows those kinds of formulas to be evaluated in a real-time operating system. And so, so in terms of the pipeline, you have telemetry data coming in, specific telemetry parameters or signals that are sent on a sample by sample basis to the atomic checker. The atomic checker converts them into Booleans. The Booleans are processed by the inference engine, which evaluates whether or not the temporal logic formulas that you've specified hold. And what it outputs is a set of verdicts. And the verdicts can be, there's basically essentially three possible outputs for the verdicts. One is the contract is not being evaluated because the assumption has not been met yet. Another possible verdict is it's invalid, which means that the assumption is satisfied, but your contract, but your guarantee does not hold. Something is being violated. Okay, the system is not satisfying your contract. Or the third verdict, which is the one that we hope for most of the time, is that we're good, right? The contract is, the assumption's met and the guarantee is met, and the system is good. Now, one of the benefits of R2U2 is that it can be used offline and online. The offline mode is a good mode for us to kind of check out the MLTL formulas, the filter commands, make sure everything is working okay. The way that works is we specify the formulas and the filter commands in an MLTL file format, and we use a parser to parse that MLTL file to generate a set of binaries that's going to drive the R2U2 executable. In the case of offline, again, this is something that we use to check out and make sure that we've got our MLTL formulas and the filter commands correct, is we can simulate the input stream using a CSV file format. So we can sort of create different kinds of scenarios using that CSV file format and then test our MLTL to make sure that it's correct in offline mode. And the outputs there are sent to the console. So we can, and they also put in a log file. So we can run different kinds of scenarios and evaluate to make sure that the linear temporal logic formulas that we're using are correct. Then we go to the online implementation. So in there, I mentioned the runtime monitor can use the same binaries. So the binaries that we've generated and tested in offline mode, the same binaries are used for the online or the real-time flight software. So there's no difference between them. We're not changing that. So once we've checked out the MLTL in the offline mode, we can be confident that it's going to work in runtime. So the runtime monitor extracts the input telemetry from input stream from telemetry, and then there's a set of library functions that are provided to pass that input stream one sample at a time into the R2U2 inference engine, which evaluates the temporal logic formulas and then outputs this verdict stream. One of the decisions that we needed to make was, are we going to allow R2U2 to take any action, or the runtime monitor? So the architecture, the way that VSM is set up, is that we have a fault management engine which both detects faults and takes action on faults. So the decision that we made was R2U2 is not going to do anything by itself, because we want to think of this as kind of an independent, separate monitor, to have a sort of something that separately made, so that we know that we don't have to worry about it doing something wrong in the sense of taking actions. But the verdicts are passed to the fault manager application, and the fault manager application is informed by data on what actions it should take if there are contract violations. And so the fault manager is the one that actually will do things like, for example, set alerts or take actually some action based on contract violations. Okay, so just to kind of wrap up what we've been able to achieve. So we've been working on this now for about 3 years. We have progressively gone from sort of defining how we were going to go about doing it, to selecting the tools. We've implemented a number of different contracts. We have tested R2U2 in certainly offline, but also In online environments, we've tested in a Linux environment and also on a target processor, the SP0, running under VxWorks. In both environments, it's worked really well. We've evaluated a number of different contracts and tested them and implemented them. We've also sort of refined and honed the workflows about how we're going to go through defining contracts, checking out the contracts, then implementing them on the target. That workflow has been validated, and we consider RTU2 to be something that we are envisioning implementing in the actual flight software that's going to fly for the co-manifested vehicle. There's also some future work. As we've gone through this process, we've identified some potential enhancements, and we're very thankful that Iowa State University has been very receptive to be able to implement some of these enhancements that we've requested. One of the things we're working on right now is something dynamic set operator contracts. So a normal contract usually takes one input stream or a set of input streams in a single temporal formula that applies to one input stream. There are things that we use or constructs that we use within VSM where there are multiple things that happen concurrently. So an example would be if there's an activity that we want to do an operational contract on. If there's a potential that there could be multiple activities in parallel, we want a given safety property to hold across a full set of activities instead of just one activity at a time. We've requested an enhancement to RTU to allow us to specify a single formula that can apply to the full set of activities and evaluate the full set of activities as a whole as opposed to one at a time. And so we call that dynamic set operators, and we're working on that. We're also working on some runtime optimizations because we want R2U2 to run as fast as possible in the real-time environment. And then because this is going to be implemented on NASA flight software, we've asked for some documentation and support tools. Okay, so that's my talk on assumed guarantee contracts and operational verification, and be happy to take questions.